Okay, guys, nothing new in this lesson, just those application questions that we all know and love. So um, today's goal, I can solve polynomial inequalities and equations in context with and without technology. I think we're just going to use technology for both actually today. Yeah. We're dealing with some really big numbers. All right, so example 1, we're jumping right into it. So the volume V in cubic centimeters of a block of ice, so a huge block of ice that a sculptor uses to carve the wings of a dragon. Okay, so they're using this block of ice to carve the wings of a dragon, can be modeled by V at x is equal to 9x cubed plus 60x squared plus 24 9x, where x represents the thickness of the block in centimeters. So what maximum thickness of wings can be carved from a block of ice with volume 2,532 centimeters cubed? Now, this is assuming that they will make the thickness of the wings the same as the thickness of the block, right? So they're going to use like right edge to edge of the block. So really, like when it says what maximum thickness of wings can be carved from a block of ice with this volume, we also want to know like what maximum thickness of the block of ice, okay? Because that's what x represents. X represents the thickness of the block. All right, so to start this question, we want to know a few things. We want to know well, let's set this up here. So the volume is just 2,532. So volume is equal to all of this. So we are going to say, when will 9x cubed plus 60x squared plus 249x equal, okay, this function represents the volume. When will the volume, for what values of x will we get a volume of 2,532 centimeters cubed? Okay, so the first thing we're going to do is set volume equal to that amount, therefore setting the function equal to that amount. Okay, so now we want to always, when we're solving, we could solve it just like this, but we are, we've been practicing, let's isolate 0 on one side. So we're just going to subtract 2,532 from both sides. So we're left with this new function, 9x cubed plus 60x squared plus 249x minus 2,532 is equal to 0. All right, so now we are solving this function. Rather than when will the volume function be equal to a volume of 2,532, we've created a new function and we want to know when will this function be equal to 0. In other words, we want to know the x-intercepts, okay? So want to know x-intercepts. The x-intercepts of this new function are also the solutions for this equation here. These equations are the same, we've just moved it over. All right, so if we want to know when f at x is equal to 0, we're just going to put this function into our Desmos graphing calculator. So we have, I think I already put this in here, 9x cubed, yeah, this one here. So let's shut all these ones off. And this is way zoomed out. Well, actually zoomed in and way up high. All right, so this is what it looks like, which doesn't really look like much of anything. The more you zoom out, it just looks like a straight line. And we would have to zoom in and in and in and in and in to figure out what value of x provides a function value of 0, and I'm like, that doesn't make any sense at all. It's because we didn't have our minus 2,532. I remember I was going to show you guys two different ways. So, okay, so way 1, is we've isolated that function, we put that exact function in, and our solution is quite literally just here. There's only one of them. There's only one value of x that will provide a function value of 0, and that is when x is equal to 4. And so we could go back and we could say at x equals 4. Okay, and I will go back to Desmos and show you the other way. So that was at x equals 4. Or we could say f at 4 equals 0, but at x equals 4. So therefore, a wing thickness of 4 centimeters would, or could, I should say, could be carved. That's the maximum we could do. Could be carved from a block of ice with volume 2,532 centimeters cubed. And again, we're making some assumptions here. We're assuming that they carved the wings the entire thickness of the block of ice, that the x represents the thickness of the block, and that the wings are carved to be just as thick as the block of ice. And so that's why we're saying that a wing thickness of 4 centimeters, because that's the thickness of the block of ice. So a couple things we could do, cool things on Desmos. We could go back to the original function here, and let's call this v at x. Does it like that? It might not want me to do that. It does like f at x. Okay, there we go. So v at x. And then the original function was this. And we could add a line here that says, well, what if we do v at 4? That's multiplying that. And notice how we get the exact volume. So we know that this is the volume per the thickness, and when we have a thickness of 4, the volume is equal to 2,532. So this is just us checking our work. The other thing we can do is, if we did put the original function in without the minus 2,532, okay, so just we want to know when will this, for what value of x will this original function have a function value of 2,532. If you go in Desmos and you type y equals 2,532, it will, y equals anything is just a vertical line. If I did right now y equals 1, a horizontal line. The result will be a horizontal line at y equals 1. If I did y equals 2, now my horizontal line is up there. So when I do y equals 2,532, it will draw a horizontal line on my graph, and the benefit to this is somewhere on this graph is this function. Now we don't see it, but it's here, that green line, now we see it. And if we go all the way up here to, and that's why I was zoomed way out before, 2,532, that's the point. The benefit of this is I can just click on either one of these functions and their point of interception will appear. And now I can see that an x value of 4 will yield a y value of 2,532. So if you absolutely hate that, then you can just stick with your minus 2,532 and viewing what your x-intercept is. All right, and one other question. So an open top box can be made from a sheet of aluminum measuring 50 centimeters by 30 centimeters. So let's maybe draw a diagram here. So what we know is that this is 50 centimeters and this is 30 centimeters. And it said that what we're doing is we're trying to make an open top box. So we want to fold all the sides up so that we're left with like some little open top box. And how we can do that is by cutting congruent squares, meaning the same size squares from the 4 corners. So if we go back here to our square, and if we do this, we could say, okay, we would be cutting out a square from each corner, and they have to be the same so that when that one's not exactly right on the corner. That's going to bother me. So when we cut these out, and we go to fold the tabs up. I know this is hard to visualize, but this line here and this line here are just going to meet perfectly straight up, and we could just put a little piece of tape, and we would have an open top box without all of the overlap and trying to fold and figure out what to do with the extra paper on the corners. They would just be gone. So this is kind of what this would look like here. And so write a polynomial function to represent the volume of the box. So regardless whether it's open top or not, that doesn't change the volume of this is the rectangular prism. We can fit the same amount of stuff in it, assuming that we're only filling it flush with the edges of the sides, whether it has a top or not. So just a reminder, volume of a rectangular prism is length times width times height. So in order to create a polynomial function to represent the volume of this, we need to define each of these: the length, the width, and the height. So the length of this box, the length of this piece of aluminum is 50 centimeters, but by the time we cut this out and cut this out, so let's call this X. Okay, this is an X by X box, and we're cutting the same size because we want the sides to line up perfectly, which means that all of these squares are X by X and X by X and X by X and so on and so forth. It doesn't really matter which sides I label. So the length of the box is actually going to be from here to here because we will have cut these off and folded the sides up. So that means the length of the open top box is going to be 50 centimeters minus 2 times whatever we decide X is, because we might make X 1 centimeter and 1 centimeter, and then our length of our box is going to be 48 centimeters. But if we go and make it 2 centimeters and 2 centimeters, then maybe it's 46 centimeters. So we don't know. X is variable, so we just leave it as variable. Same thing with the width. The width is going to be 30 less whatever we decide X is going to be, and 2 of those X's. And the height of the box, it will always work out to be whatever X is. So the height will always be X. And just to kind of show you too, so if we were to make this box really big, we could do that. But then when we cut this out, and then if we were to copy and paste this down here, well, it would be a very, 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 very skinny box, but it would be high, right? The box would be really, really high. So as we change the dimensions, the height of the box, as we change X, that impacts both the width and that impacts the length of the box. Okay, so the height is just X, and the width is 30 minus 2X, and the length is 50 minus 2X. And so our polynomial function, and this is to represent the volume of the box, so we could say V at X is equal to length, which is 50 minus 2x multiplied by width, which is 30 minus 2x multiplied by height, which is just x. And I would probably rewrite this with my x in front. X times 50 minus 2x times 30 minus 2x. Okay, so far we have written a polynomial function to represent the volume of the box. Check. And then use it to determine the dimensions that result in a volume that is greater than 4,000 centimeters cubed. All right, so we now want to know when this function, x times 50 minus 2x times 30 minus 2x is greater than 4,000. So we are going to go back over to Desmos, and I believe I already put it in here. So there's our function. Let's turn these ones off. X times 50 minus 2x times 30 minus 2x. Let's turn that function back on. So here we have our function that represents the volume of that box, and we want to know for what values will it have a volume of exactly 4,000. So I'm going to use this y equals approach, and I'm going to scroll up here to see what my intercepts are, the point of interception between that horizontal line and my function. We're almost there. And I'll probably show you the other way as well. When y equals 4,000, where's my line? I have to turn it on. Duh. Okay, so when y equals 4,000. So we have some options here. Without seeing this function, it's hard to, but there you can see that this is coming up and going down. Okay, so this is where it is greater than 4,000. Anything beyond here is less than. So the points where it's greater than 4,000 are between here, and then again over here. Okay, and so here, this is when x is 5. Okay, this is when x is 7.19. And this over here is when x is 27.8. So x, I'm going to write these down, 5, 7.19, and 27.18. And let's go back over here and just talk about this. So when, let's just write values of x that result in a volume greater than 4,000 centimeters cubed, I think it was centimeters, yeah, are when x is between 5 and 7.19, inclusive of those, that's exactly equal to 4,000 at those points, and from 27.81 all the way up until infinity. Now, here's the thing. This function is modeling the volume, but it does not mean that the domain in the context of this question is anything that we want it to be. So we have to think critically. Is it possible that x, remember that these values represent x, that x could be 27.81? If we go back up here, if we made this square so big that the value of x was 27.81 centimeters, and then we doubled that, oh, now what have we done? And we double it and we put it on this side, we'd have to make it even bigger. We would be left with no length and no width. The length, like if we had x as 25, for example, then we would be left with no length at all, right? It can't be that big. And width is like, we can't take away 27.81 two times from 30. We can't take away 27.81 two times from either one of 30 or from 50. Okay, so sometimes when you're dealing with word problems, the equation that you come up with does model the situation, but not over all values of x. So because of that, we could conclude that this is not a possible solution. Therefore, values of x that yield or that result in a volume of exactly, or result in a volume greater than 4,000 are, and we could write it in interval notation if we want, when x is between 5 and 7.19. Okay, so there is the answer to that question. Now I will say that we technically didn't answer this question because it says, and then use it to determine the dimensions that result in a volume greater than 4,000. In order for us to do that, we would actually have to sub back in a value for x to figure out the dimensions, as in what would the length be, what would the width be, what would the height be. The thing is, there are infinitely many possible answers here. It all depends. As we change x, then the height changes, the width changes, and the length changes. And x can be quite literally any rational number that we want. No, any real number between 5 and 7.19. So it's not like these are the only two solutions. Those are the only two solutions that result in exactly a volume of 4,000 centimeters cubed. But any solutions that result in a volume greater than 4,000 is any x value between this, meaning we could cut a centimeter, a box with a side length centimeter of 5 centimeters, 5.1, 5.2, 5.5. We could go on and on all the way up to 7.19. Okay? All right, guys, that's it for this lesson, and there's some practice questions for you from the textbook, our favorite word problems, and I'm going to end this video in under 20 minutes. Yay!